Hello, everyone. I'm Olympia. Thank you for being here with me in this wonderful place called Lights Out Library, and I have a great story to tell you. Tonight, we're going to continue and conclude our review of all the elements in the periodic table. We already went through elements 1, hydrogen, to 29, copper, in the first two parts of this story. We have almost 90 more elements to cover. As we're going to see, many of them are less familiar and less significant in our daily lives, in biology or in industry. Some are even absent from nature. They do not occur naturally and only exist in laboratories. So we will go through some of them more quickly. But there are still plenty of elements like gold, silver, uranium, that call for lengthier introductions. But first, I would like to let you know that we have a Patreon page for those of you who wish to and can support this project, get more from it, and listen ad-free on your favorite podcast app. Patreon is a platform that allows you to contribute directly to our work financially. Our least expensive tier is $3.50 per month, but it doesn't mean you will get less. We let people contribute what they wish or can, and everyone gets everything that is on our page, because the world is a better place when the sun shines for everyone. You will gain access to 26 exclusive episodes. We add a new one every month, and you can listen to and download all the episodes with and without background sounds. And as a token of gratitude, we offer advance releases to our patrons. We have added links to Patreon as well as links to different streaming options, which may be better suited for you. You will find them in the description of the episode. And now, before we begin, if you wish to, you may close your eyes and allow yourself to forget about any worries. Assume a comfortable position. Maybe move a bit to settle. Take a long, deep, relaxing breath. And when you slowly exhale, feel your shoulders drop. Release the tension in your neck. Let your face soften and your jaw relax. Make sure your fingers are not clenched and that your legs are relaxed too. And allow the sound of my voice to guide you through this journey. Let's get started with element number 30, zinc. Zinc is a metal that in some respects is chemically similar to its predecessor in the same group, magnesium. I already told you before how different metals are obtained from ore by smelting or electrolysis, as in the case of aluminum. But how is ore sorted? When ore is extracted from a mine, it is not pure, and from one site to another, the type of ore that is taken from the ground and the elements it contains can be very different. So the first step before the ore can even be processed is to separate it from the surrounding rock that will be discarded. There are different ways of doing this. It can be done by crushing and smelting, which is the usual treatment for iron ores. Another method used especially for copper, precious metals, and uranium is called heap leaching. It uses a series of chemical reactions that dissolve specific minerals so that the desired one or ones are progressively separated and become usable. But the modern refining of zinc doesn't use these processes. It is achieved via another process called froth flotation. Froth flotation is a process that separates minerals from worthless materials by exploiting their hydrophobicity, how strongly they are attracted to or repelled by water. You know what hydrophobic and its opposite, hydrophilic, mean. A hydrophobic material is one that is repelled by water and will not get wet or mix with water easily. Oil, for example, is hydrophobic. Hydrophilic is the opposite. A hydrophilic material gets wet or dissolves very easily in water. Table salt, for example, is a typically hydrophilic compound. So the concept of froth flotation is to apply different wetting agents to ore and separate it based on what floats and what does not. In this way, it is possible to create an industrial process that can automatically separate large quantities of raw material, in this case, material produced by mining. But froth flotation is also used in other areas and processes, such as wastewater treatment and paper recycling. It is not limited to mining. The development and industrialization of froth flotation in the 20th century greatly enabled the use of ores that had not previously been rich enough to exploit. Many mines simply could not have existed without it, or would have been much more expensive to operate, because the ore they produced was not rich enough to be exploited. So this is how zinc ore is typically separated. Then it is roasted at high temperatures to purify it, because it generally comes associated with sulfur in zinc sulfides. Finally, when most sulfur is gone, it is put in a solution to be obtained pure using electricity, like for aluminum. Zinc is resistant to corrosion and also relatively light, which is why it used to be employed to cover roofs. It still is sometimes, or to make gutters, but it tends to be replaced in that role nowadays by plastics or other elements that can even be lighter and also resistant to corrosion. In biology, zinc is also an essential element to life, for microorganisms to plants to animals. Like for a few other metals, life has evolved on Earth using the properties of zinc extensively. So, like calcium or iron, you find it in a lot of bricks that are essential to biological life. It is present in every single class of enzyme. You remember what enzymes are. They are very important to life because they act as catalysts that make many chemical reactions necessary to life happen. Finally, in our immediate environment, zinc is also in brass. Its alloy with copper, brass, was already in use thousands of years ago during the Bronze Age. It could work as a substitute to bronze when zinc rather than tin was available, except brass is softer than bronze, so it is not suitable for tools or weapons when it contains relatively more copper. Brass tends to be bright and gold-like. This is why it is often used for doorknobs or drawer pulls. You probably have more brass, and therefore zinc, around you than you think. It is also common in zippers and plumbing because it resists well to corrosion, or in electrical plugs and sockets. Let's move on to element number 31, Gallium, and element number 32, germanium, which are used mainly in electronics. Their properties are somewhat comparable to those of aluminum and silicon, respectively, but they are far less abundant and harder to collect, which is why they are mainly used in small quantities for electronic applications. Both gallium and germanium are also called metalloids. So what is that? It is somewhat like the concept of a semiconductor. Metalloids are elements that have some properties similar to those of metals and others similar to those of nonmetals. They are in between. But we saw before that the concept of a metal itself was imprecise, because what defines a metal? The capacity to conduct heat and electricity can change depending on the conditions, and under certain conditions of pressure and temperature, many elements become conductive, even hydrogen. As I mentioned before, metallic hydrogen is thought to be present in large quantities inside gas giant planets like Jupiter and Saturn. And metallic hydrogen is simply hydrogen made electrically conductive, metallic, by the extreme pressure and temperature inside these planets. So the boundaries and definitions of metalloids are also somewhat imprecise. They lack specificity. But the term is still used in chemistry literature, and some elements are still often called metalloids. Among the elements we have already reviewed, boron and silicon are examples. Sometimes other elements like carbon and aluminum are also included in the group of metalloids. But this is much more controversial because many chemists prefer to consider them a nonmetal and a metal, respectively. So as you can see, the concept of metalloids is not very specific or well defined. But if you come across it, the concept behind it is that metalloid is an element that has some of the characteristics of metals without being one. Element 33 is known for its toxicity. It's arsenic, another metalloid, by the way. Arsenic has been known as a poison for centuries, thousands of years, in fact, since antiquity. The name arsenic comes from a word in Syriac, a language that was spoken in the Levant 2,000 years ago. It was adopted into Greek as arsenikon, then into Latin as arsenicum. From there, it became arsenic in French and passed into English as arsenic. As an element, it is sometimes used in alloys. This is not a recent use. During the Bronze Age, some cultures already added a small amount of arsenic to copper alloys to make them harder. In industrial times, it was added to many products, such as insecticides and herbicides and products used to treat wood, because of its ability to eliminate biological life. All these applications have tended to decline in recent decades as the toxicity of arsenic has become more widely recognized. Arsenic poisoning can be rapid if a massive dose is ingested, or progressive over a long period if someone is constantly exposed to even small doses. It is very potent. But why is it so toxic? Because arsenic oxides have an affinity for compounds located at the active sites of many enzymes. This disrupts the proper functioning of cells and leads to their death. So the signs of arsenic poisoning are not very specific. The death of cells can cause multiple organ failure. That is why, until the Middle Ages, arsenic was a poison of choice for discreetly killing a person. It was very difficult to determine the exact cause of death. Poisoning might be suspected, obviously, but it was difficult to prove. Later, tests were developed, and arsenic poisoning can now be identified much more easily. But the bad reputation of this element in relation to health was established, and rightly so. Element 34, selenium, is also toxic in small doses. Trace amounts of selenium are necessary for cellular function in many animals, including humans, but the level of toxicity is low. However, selenium is less abundant than arsenic, and that is why poisoning is very unlikely, except near places where it can bioaccumulate in certain aquatic habitats, for example, near chemical plants, or as a result of farming. In these cases, selenium may accumulate in plankton or fish in wetlands or ponds and become dangerous if the fish are consumed by humans. Number 35, bromine, is the next element after fluorine and chlorine in the same group, called the halogens. I already told you about fluorine and chlorine. One distinct feature of bromine is that under standard conditions of temperature and pressure, it is a reddish-brown liquid. This is unusual because out of 118 elements, only 2 are liquid under normal conditions: mercury and bromine. Of course, there are plenty of liquids around us, starting with water, but these liquids are compounds or molecules. If you separate water into oxygen and hydrogen, these 2 elements will be gases under normal conditions. Number 36 is krypton, yet another rare gas after the ones we have already discussed: helium, neon, and argon. Like them, it is a colorless and odorless gas that occurs in trace amounts in the atmosphere, and it is used in fluorescent lamps for the same reason as its predecessors. Like other noble gases, it is very unreactive. The elements that follow also share properties with their respective cousins in the same group. Rubidium. Number 37 is the next alkali metal after potassium, sodium, and lithium. One difference between rubidium and these elements is that it is denser with water, so it does not dissolve in it as easily. Instead, it tends to sink in water. Then there is strontium, number 38. Natural strontium is generally not hazardous to health because it is found mainly as a stable isotope, strontium-88. Remember what 88 means? It has 38 protons in its nucleus. It is element number 38 plus 50 neutrons for a total of 88 particles. But there is one isotope, strontium-90, with 2 or more neutrons, and it is a dreaded product of nuclear fallout. Strontium-90 appears as a result of the fission of larger atoms, the kind of fission that provides the energy for nuclear reaction. And strontium-90 is highly radioactive, which in other words means that it is unstable. Strontium-90 nuclei are not energetically comfortable with their 52 neutrons, and this is what makes elements radioactive. Because they are not perfectly stable, they tend to expel particles or energy, or even undergo fission into two or more smaller atoms, what we call radioactivity. It is the behavior, this property of emitting energy and particles spontaneously. We will elaborate on that when we cover other elements. But strontium-90 is bad news, because in addition to being radioactive, it is essentially absorbed by the human body in a similar manner to calcium, which is its predecessor in the same group. That is why this particular isotope, strontium-90, is particularly dangerous in nuclear fallout. After strontium comes element number 39, yttrium, which I already mentioned as a rare earth element. It is used in LEDs and various industrial applications, such as the production of electrodes and lasers, as well as in medical applications. Number 40 is zirconium, a metal that is used either as an additive in metallic alloys because of its resistance to corrosion, or as refractory, that is to say, because of its resistance to heat. Element 41, niobium. It is little known, and you may never have heard of it, but it is important to many technologies. It is highly resistant to heat, with a melting point close to 2,500 degrees Celsius. That is almost 1,000 degrees higher than the melting point of iron. It does not have the highest melting point of all metals. We will see that later, but it is considerably high. It is used in jet and rocket engines because of this property, as well as in many other applications in very small quantities, including optics, electronics, and the nuclear industry. It can also be used in alloys and to coat coins as an alternative to nickel. So we are surrounded by it and use it every day in very small quantities. But we barely know of this element. The elements that follow are also little known. Number 42 is molybdenum, another element with a very high melting point. It is used in alloys for this reason. Technetium, number 43, and ruthenium, number 44, are rare elements. They are also used in very small quantities in specific applications, such as nuclear medicine or as catalysts. Only a few tons are consumed annually around the world. The next one, number 45, is better known. It's rhodium. One of the rarest and most valuable precious metals. Its price can vary considerably. In 2021, an ounce of rhodium traded for an average of about 20,000 and briefly reached approximately 29,000. Today, it is averaged at 8,000. Gold averaged around 1,800 per ounce that year. So at its peak, rhodium was about 16 times more expensive than gold. But why is rhodium so sought after? There is a minor use for it in jewelry, although it is very rarely used to make pieces of pure rhodium. This is not only because of the price, because even at many times the price of gold, there would still be buyers, but also because rhodium is very difficult to work with. It has a very high melting point, and it is not malleable like gold. It is generally plated onto white gold or platinum to give these metals extra shine and a bright white surface. However, this thin layer of rhodium generally wears away with use. Jewelry represents only a small application for rhodium. A much larger quantity is used in automobile catalytic converters, where it helps reduce harmful nitrogen oxide emissions. Although manufacturers can sometimes reduce the amount they use, rhodium remains particularly effective and difficult to replace completely. Another rare and useful element is number 46, palladium. But the element that follows is much better known. It is number 47, silver. Silver has a reputation for being a precious metal, although less so than gold. Indeed, if you look at current prices to put things into perspective, it is far less expensive than gold. As of July 17, 2026, 1 ounce of rhodium was worth about $8,200, 1 ounce of gold about $4,000, 1 ounce of silver about $56. So rhodium was approximately twice the price of gold, while silver was about 72 times less expensive than gold. Silver is another metal that has been used since antiquity, together with a few other metals including gold, copper, iron, tin, lead, and mercury. If it were more abundant, silver could have a much larger industrial use and could even replace copper in some applications. Of all metals under normal conditions, it has the highest electrical and thermal conductivity. So in theory, silver electrical cables could work even better than copper cables. But this would not be practical because there is not enough silver available for use on such a scale. And by weight, silver is currently around 140 times more expensive than copper. For these reasons, replacing copper with silver on a large scale would not be financially feasible. We can move quickly through the next 3 elements. 48, cadmium. 49, indium. And 50, tin, because their properties are similar to those of their predecessors in the same groups of the table. I already told you about tin when we discussed alloys of the Bronze Age. The same can be said for antimony, number 51, tellurium, number 52, and iodine, number 53. But let's stop for a minute on the next one, xenon, number 54. Xenon is yet another noble gas, and it has an isotope, xenon 135, that is closely monitored in nuclear reactors. But why is this? Xenon 135 does not persist in nature. It is too unstable and radioactive to last for long. It is an isotope that appears during a nuclear fission reaction. Among the different elements created when nuclear fuel undergoes fission, Typically, this fuel is uranium. A common product is an isotope of iodine called iodine 135. This product of nuclear fission, iodine 135, undergoes a form of radioactivity called beta decay. I told you before that radioactivity was like an umbrella term for different phenomena in which unstable atoms emit energy in particles. Beta decay is one of these phenomena. It is a type of radioactive decay in which a nucleus emits an electron, and at the same time, a neutron becomes a proton. So when the number of protons changes, the atomic number also changes. It is no longer the same element. I just told you that iodine is number 53 in the table, with 53 protons. If it acquires one more proton, it becomes element 54, xenon. Iodine 135 and xenon 135 have the same total number of protons and neutrons in their nuclei, except that xenon has one more proton, while iodine has one more neutron. So as you now understand, xenon 135 is a byproduct of fission. Iodine 135 appears first, and it transmutes into xenon 135. But why is it relevant to the management of a nuclear reactor? Because xenon 135 has one particular characteristic. It is neutron hungry. It tends to absorb neutrons. In a nuclear reactor, that is a problem because it is the presence of neutrons that keeps the fission chain reaction going. These neutrons are available to be absorbed by heavy atoms like uranium, increasing their instability and making them undergo fission, which releases more neutrons, and so on. The reaction sustains itself as long as there is fissile material available. But if xenon 135 absorbs too many neutrons, it can slow down, inhibit, or even stop the chain reaction. This is a well-known problem in the operation of a nuclear reactor. At startup, the reactor may contain little or no xenon. But as more and more fission reactions occur during the first hours of operation, xenon 135 accumulates in the reactor as a product of fission. It starts absorbing neutrons, which inhibits the chain reaction and could eventually stop it if nothing were done. So a nuclear reactor that was turned on and left to its own devices could eventually stop by itself. This phenomenon is called xenon poisoning, and it is well known to nuclear reactor operators. To avoid xenon poisoning, the period when a reactor enters or re-enters service after fresh fuel has been loaded, or after a maintenance shutdown is closely monitored. Operators compensate for the negative impact of xenon on the chain reaction with actions that stimulate fission, such as withdrawing the control rods, which also inhibit fission inside the reactor. After a while, as xenon 135 decays, an equilibrium is reached between the production and removal of xenon 135 inside the reactor. Its quantity then remains relatively stable and does not prevent the reactor from operating. it simply becomes one of the variables involved in its normal operation. Xenon poisoning was an important factor in the chain of events that led to the Chernobyl disaster in the 1980s. The operators of the reactor that eventually melted lost control of it because they tried to stimulate the reaction inside it without correctly estimating how strongly the reactor was poisoned by xenon. They knew of this phenomenon, and under normal operating conditions, the reactor and all the rules and procedures for operating it were designed to manage it. But they were conducting an experiment on the reactor, and they deliberately disabled several safety systems that they were strictly forbidden to disable. They violated the operating rules, and they saw that the neutron flow inside the reactor was lower than they wanted. So to stimulate the reaction, they withdrew the control rods too far. Within seconds, the effects of xenon poisoning were overcome. The chain reaction grew exponentially, and the reactor became so hot that, before they could react, the control rods were expelled. All control was lost, and the energy generated by the reactor reached hundreds of times its operational limit. Following an explosion, a chemical explosion that broke open the building that contained it, the reactor and its radioactive material were exposed to the outside. A large volume of radioactive particles was ejected into the atmosphere, and the inside of the reactor's tank began to melt. That is another story, but Xenon 135 played a part in it. Staying with highly radioactive isotopes, we have cesium, element number 55, which is also an isotope, cesium 137. That is a hazardous fission product. After that, we have element number 56, barium, a metal with relatively few applications. It is sometimes used as a radiocontrast agent for X-ray imaging. It is also added to superconductors and some steel alloys. Element 57 through 71, from lanthanum to lutetium, are called lanthanides. I already told you about them when I spoke about rare earth elements. They are all part of this group, and chances are you have never heard of most of their names because they are rarely mentioned individually outside scientific or industrial settings. They include names like neodymium, number 60, promethium, number 61, europium, number 63, and ytterbium, number 70. Number 72 is hafnium. Hafnium is also a rather little-known element, but one of its applications is as a neutron absorber, a neutron catcher in the nuclear industry. I told you about Xenon 135 absorbing neutrons. Hafnium also has that capability, and this is why it is one of several materials used in the control rods of nuclear reactors. These rods are inserted into the reactor to slow it down or withdrawn to stimulate it. Hafnium slows down the chain reaction. Number 73 is tantalum, an element very similar to niobium, which we covered before. They are in the same group. the same vertical column in the periodic table, and they share certain properties. Like niobium, tantalum is highly refractory. It resists heat, and its melting point is the highest I have mentioned so far, about 3,000 degrees Celsius or 5,400 degrees Fahrenheit. That is far above the melting points of iron and copper, so it is very difficult to melt, but it does not have the highest melting point of all metals. That distinction belongs to a better-known metal, element number 74, tungsten. Tungsten melts at about 3,400 degrees Celsius, and it also has the highest boiling point of all metals, the temperature at which it turns into a gas. This boiling point is approximately 5,600 degrees Celsius, or more than 10,000 degrees Fahrenheit. Tungsten is hard and dense. We rarely get a chance to handle tungsten, but to give you an idea, it is about 1.7 times denser than lead, so it feels very heavy. This density, combined with its hardness, is the reason why it is suitable for military applications, especially armor-piercing projectiles. A tungsten tip is a good choice for piercing armor. A better-known use of tungsten, although it is disappearing from our homes, was in light bulb filaments. For most of the 20th century, incandescent light bulbs generally used tungsten filaments because of their high melting point. The electric current made the filament heat up and emit light. The inside of the bulb was filled with a noble gas, typically argon, which helped reduce the evaporation of the filament and extend its life. The atmosphere inside the bulb was also free of oxygen to prevent the filament from burning. Element number 75 is rhenium, one of the rarest elements in the Earth's crust, less than 1 part per billion. In other words, to find 1 gram of rhenium, you would have to process on average more than 1,000 tons of the Earth's crust. It has a few industrial applications, especially in jet engines, because it is used with nickel in superalloys that can withstand extremely high temperatures. The next 2 elements, osmium number 76 and iridium number 77, are known for their density. Osmium is generally considered the densest naturally occurring element. It has a density of about 22 grams per cubic centimeter. For comparison, this is almost 3 times the density of iron, twice that of lead, and 22 times that of water. Water is the benchmark for density. Said differently, for the same volume of water and osmium, the block of osmium would be 22 times heavier. Osmium is also even rarer than rhenium and is considered one of the rarest precious metals. So you might think it would be extremely expensive, but its price is difficult to establish because it has very few applications and is traded only in very small quantities. It does not look particularly shiny. It is simply silvery, like many other metals. Iridium is somewhat more common, but still little known. World production of iridium is only several tons per year. That is really not much. But the element that follows, number 78, is much better known. It is platinum. In monetary terms, platinum is currently less expensive than gold, but there was a time when it was worth up to twice as much, and it remains a precious metal with a silvery white appearance. It has more industrial applications than gold, and its most remarkable characteristic is that it is one of the least reactive metals. Metals that do not react easily can sometimes be found in their native form in nature, which is logical. They have not combined with other elements. Gold and others we have reviewed, such as rhodium, palladium, and osmium, share this characteristic. They are sometimes called noble metals because they are relatively unreactive, somewhat like the noble gases. And gold is the next one, number 79. Some of the characteristics that contribute to the appeal of gold, such as its resistance to corrosion, which allows it to remain shiny, comes from its low reactivity. It is also resistant to most acids. The exception is aqua regia, the mixture of hydrochloric and nitric acids that we talked about earlier. Gold is relatively rare, but many elements are rarer than gold. Its high monetary value comes from a combination of its visual appeal. It does not tarnish easily, and unlike most metals, it has a distinctive yellow color, and the reputation it has acquired as a precious material after several thousands of years as a symbol of wealth and power around the world. This did not happen in every single culture, but in many of them. From the Americas to Africa, Europe, and Asia, gold acquired a particular status, enough to make it an important symbol of value. More than 90% of the demand for gold is linked to jewelry, investments, and central bank reserves. According to global figures for 2025, about 33% of gold demand went to jewelry fabrication, 44% to investment, and 17% to central banks. Only about 6% went to technology and other industrial applications, mainly electronics. Small quantities are found in many computers and are also used in dental restorations and for gilding ornaments. Part of the gold used in jewelry is also intended as a way of storing value. I do have a story that covers a fascinating history of gold that you can find in my library. We still have a few better-known elements to go through, such as the next one, number 80, mercury. I told you earlier about bromine and mercury are the only two elements known to be liquid under normal conditions. Mercury is the only metal of the two, because bromine is not a metal. It has various familiar uses, such as in thermometers, although this use has declined, and it is also known as a toxic environmental pollutant. Heavy metal is another concept that is loosely defined. It can refer to the density of metals as opposed to lighter metals like aluminum, and in that case, mercury is a heavy metal. It is quite dense. In health and environmental terms, the expression is often applied to elements that can be highly toxic, either in the elemental form or as part of compounds, and that can accumulate in the environment or the food chain. Mercury is one of them, together with lead, cadmium, arsenic, and certain forms of chromium. I have already highlighted the toxicity of them. Mercury in particular can cause damage to the central nervous system. Another highly toxic element, particularly in the form of salts, is thallium, number 81. It was used in some historical poisonings as an alternative to arsenic. Because it is highly toxic and its compounds can be difficult to detect without testing, thallium is sometimes called the poisoner's poison. Number 82 is also toxic. It is another heavy metal that has probably caused harm on a much larger scale than arsenic and the other toxic elements I mentioned before. Lead. Lead was historically relatively abundant and easy to extract. It has a high density and melts at a very low temperature, just over 300 degrees Celsius. This made it a metal of choice. It was inexpensive, easy to work with, and suitable for a wide range of applications in construction, plumbing, paints, batteries, and as an additive to gasoline. Its toxicity has been known since at least the time of the ancient Greeks and Romans, who documented it. Lead poisoning caused a syndrome called Saturnism, but its dangers were downplayed for a long time. I remember that when I was a child, lead was still used in toys, such as little soldiers and figurines, as well as in plumbing. Many of the uses have now been prohibited or severely restricted, but they were still common in the 1970s and 1980s. Lead is a potent neurotoxin that damages the nervous system and accumulates in bones and teeth. Its effects are not always immediately apparent, but over time, it can affect a person's general health. It can damage the cardiovascular system and kidneys, and it is best known for causing neurological and developmental problems. Element 83 is bismuth, a metal that can sometimes be used as a replacement for lead because it is far less toxic. After that, with element number 84, polonium, we enter the territory of heavy atoms. The further we advance, the more protons they have, and the more neutrons they also tend to have in their various isotopes. So they become heavier and heavier. Heavy atoms have a tendency to be unstable. That is to say, they decay and emit particles and radiation. I mentioned earlier radioactive beta decay, with the example of iodine 135 turning into xenon 135 in nuclear reactors. Beta decay is when an atom emits an electron, or its opposite, a proton, and a neutron becomes a proton. Another type of radioactive decay is alpha decay. This is when the nucleus emits what is called an alpha particle, or a helium nucleus, 2 protons and 2 neutrons. The instability of an atom may lead to radioactive decay or even fission, when the nucleus breaks apart into 2 or more atoms with smaller atomic numbers. So under the umbrella of radioactivity, we have different phenomena that occur at the atomic level and lead to the emission of radiation, energy, and particles of different types and sizes. These can include protons, neutrons, and electrons. From polonium onward, all atoms have varying degrees of instability. Sometimes this instability is not very pronounced, and they decay very slowly over millions of years. At other times, they are very unstable. This depends on the elements and their respective isotopes. But unlike the lighter elements that we have just gone through, which can have radioactive isotopes and other isotopes that are not radioactive, above atomic number 83, all elements are radioactive to some extent, and it begins strongly with polonium, which has only highly radioactive isotopes. The discovery of polonium in 1898 was one of the discoveries that established Marie Curie's reputation. This is why it is called Polonium after Poland, her country of birth. She became the most prominent of the early explorers of radioactivity, a phenomenon that was barely understood in the 19th century. Element number 85 is astatine, which is the rarest naturally occurring element in the Earth's crust. Why is that? Because it appears only in tiny quantities as a decay product of heavier elements, and all of its isotopes are short-lived. The most stable one has the half-life of about 8 hours. Half-life is a concept used to describe the radioactivity of isotopes. It is the time it takes for half of a quantity of radioactive material to decay. So a half-life of 8 hours means that after 8 hours, half of a given quantity will have decayed. That is short. Half-lives can range from fractions of a second to billions of years. In general, the shorter the half-life, the more rapidly the isotope decays. The consequence of this instability and extreme rarity is that no large sample of astatine has ever been gathered. Only tiny quantities have been produced and studied, so we do not know with certainty what a sample of astatine would look like under normal conditions, although it is expected to be a solid. After astatine comes a noble gas, number 86, radon, which is also radioactive in all of its isotopes. Unlike its predecessors in the group of noble gases, the longest-lived common natural isotope, radon-222, has a half-life of almost 4 days. That remains short, but radon is continuously produced in nature by the decay of heavier elements such as uranium and rhodium. After it come several more radioactive elements. Number 87, francium. Number 88, radium, another discovery associated with Marie Curie. Number 89, actinium. Number 90, thorium, which is more stable than its neighbors in the table. Thorium is still radioactive, but it has one isotope, thorium-232, 90 protons plus 142 neutrons, with a very long half-life of about 14 billion years, close to the estimated age of the universe. So this particular isotope decays very slowly, although concentrated thorium can still present health risks and must be handled with appropriate precautions. Thorium also has a few industrial applications. Number 91 is called protactinium, and after it come the last two elements in the table with a certain degree of fame. Number 92, uranium, and number 94, plutonium. Between them is neptunium, number 93. Uranium is a common fuel for nuclear power plants and some nuclear weapons. But why is that? Because some isotopes of uranium, especially uranium-233 and uranium-235, can maintain a sustained nuclear reaction when they are present in sufficient concentrations, and their fission creates all the byproducts that appear in the reactor. Uranium was naturally present on Earth in sufficient quantities to support an industry based on it. Most uranium available in nature is the isotope uranium-238, although it also contains a small amount of uranium-235. For most nuclear reactors, uranium must be processed, enriched in uranium-235, before it becomes usable as nuclear fuel, because uranium-238 does not undergo fission as easily. Plutonium, number 94, is the last element that can occur naturally without human intervention, although only in very small quantities. Almost all the plutonium used today is produced artificially through transmutation in nuclear reactors. Uranium atoms are transformed into plutonium, increasing their atomic number by 2. This is also what made uranium appealing for military use in nuclear weapons. Uranium-238 is said to be fertile because it can be turned into plutonium, and plutonium is particularly prone to participating in fission chain reactions. Some of the first atomic bombs already had plutonium cores. After plutonium, all the elements from number 95, Americium, to 118, Oganesson, were first obtained artificially after their properties had been theorized. They are generally very unstable. These are enormous atoms with hundreds of particles in their nuclei. So to conclude our talk for tonight, I will go through the numbers and names. It is a bit like counting sheep. Let's begin. We have number 95, Americium, number 96, Curium, 97, Berkelium, 98, Californium, 99, Einsteinium, 100, Fermium, 101, Mendelevium, 102, Nobelium, 103, Lawrencium, 104, Rutherfordium, 105, Dubnium, 106, Seaborgium, 107, Borium, 108, Hassium, 109, Meitnerium, 110, Darmstadtium, 111, Roentgenium, 112, Copernicium, 113, Nihonium, 114, Larivium, 115, Moscovium, 116, Livermorium, 117, Tennessine, 118, Oganesson. We have finally completed our tour of the periodic table of elements. I hope you enjoyed this little exploration journey of the elements. Now you can let go and sleep. Or If you are not sleepy yet, you may pick another story from my ever-growing library. And until we meet again, good night. Sleep well.